The seafloor stretches beneath us as a dynamic interface, a place where geology and biology come together in an endless conversation deep below the ocean surface. It is a realm of constant change, of forces that work on scales both vast and intimate, shaping the very foundation upon which the waters rest. When we think of exploration, we often imagine distant planets or the farthest reaches of space, yet nearly 3/4 of the global seafloor remains unmapped, its geological details hidden in darkness, waiting to tell their stories to those willing to listen. The ocean floor is not a static place, not a simple basin that merely collects what falls from above. It is alive with movement, with creation and destruction happening in a grand cycle that has continued for hundreds of millions of years. At the heart of this dynamic system lies the oceanic crust itself, a layer that forms continuously at ridges while simultaneously subducting at trenches, maintaining a thickness that typically ranges from 5 to 10 kilometers. This crust is not uniform, not identical from one place to another, but it follows patterns that reveal the fundamental nature of our planet's outer shell. When we measure the oceanic crust carefully, we find it averages 6 to 7 kilometers thick, a relatively thin skin compared to the thick continental masses, and it is composed mainly of basalt and gabbro, rocks that crystallize from molten material rising from the mantle below. These rocks tell us about temperatures and pressures, about the chemistry of the Earth's interior, about processes that occur in places no human eye has ever witnessed directly. The oceanic crust distinguishes itself from its continental counterpart in important ways. It is thinner, yes, but also denser, and this density comes from its mafic composition, rich in magnesium and iron, elements that make the rocks heavy and dark. This difference in composition is not merely academic. It drives the great tectonic engine of our planet, determining which parts of the crust will sink and which will ride high. Beneath this oceanic crust, at a depth of 5 to 10 kilometers below the seafloor under normal oceanic conditions, we find the Moho discontinuity, the boundary between crust and mantle first detected by studying how earthquake waves change speed as they pass through different materials. The Moho represents a fundamental change in rock type, a transition from the basaltic and gabbroic rocks above to the peridotites of the upper mantle below. When geologists measure the specific gravity of oceanic basalts, they find values ranging from 2.9 to 3.4, numbers that confirm these rocks are denser than the continental granites and sedimentary rocks that average closer to 2.7. This density difference of just a few tenths may seem small, but it has profound consequences for the way plates interact, for the way mountains rise and ocean basins sink. In the Atlantic Ocean, the seafloor carries a geological youth about it. Most of the Atlantic seafloor is younger than 60 million years, a consequence of ongoing spreading that continues to push the Americas away from Europe and Africa at rates we can now measure with satellites. This young age tells us that the Atlantic is still growing, still in an expansive phase of its existence, unlike some ancient ocean basins that have long since been consumed. The rock record preserved in the deep ocean is extraordinary in its completeness and clarity. It preserves Earth's tectonic engine in motion, capturing in stone the processes of creation at ridges and destruction at trenches. When we drill into the seafloor or sample it with submersibles, we are reading a book written in basalt and sediment, a chronicle of plate movements, of magnetic field reversals, of changes in ocean chemistry and climate. Seafloor spreading, that process discovered and confirmed in the 1960s, recycles crust through subduction elsewhere on the planet, maintaining a balance between creation and destruction that keeps the total surface area of the Earth constant. What rises at the mid-ocean ridges must eventually descend at the trenches, returning to the mantle to be melted and transformed, only to rise again in some future epoch. Where the continents meet the oceans, we find continental margins, transitional zones that mark the shift from land to deep ocean basins. These margins are not simple slopes but complex geological provinces with their own characteristic features and processes. Carved into the continental slopes are submarine canyons, steep V-shaped valleys that can rival the great river canyons on land in their scale and drama. These canyons serve as conduits, channeling sediments from the shallow continental shelf down into the abyss, cutting through rock over millions of years through processes both gradual and catastrophic. The continental slopes are not stable. They are prone to failure on scales that dwarf any landslide witnessed on land. Submarine landslides can displace up to 600 cubic kilometers of material along these margins, events that happen suddenly, perhaps triggered by earthquakes or the simple accumulation of unstable sediment reaching a critical threshold. When these slope failures occur, they generate turbidity currents, dense mixtures of sediment and water that flow down the continental slope like underwater avalanches. These currents eventually slow and deposit their loads as turbidites, creating graded beds where the coarsest particles settle first and the finest last, producing a characteristic sequence that geologists can recognize in ancient rocks now uplifted onto land. The sediments that accumulate on the seafloor come from many sources. Terrigenous sediments originate from continental erosion, the slow wearing down of mountains and plains carried to the sea by rivers, by wind that blows dust far offshore, and by currents that redistribute material along the bottom. These land-derived particles mix with material produced in the ocean itself, creating hemipelagic sediments that combine both terrestrial and biological components in varying proportions depending on location and depth and productivity of the overlying waters. In certain tectonic settings, particularly at subduction zones, we find forearc basins, depressions that trap sediments between the deep trench and the volcanic arc that rises behind it. These basins can accumulate kilometers of sediment over time, building thick sequences that record the history of the subduction system and the erosion of the volcanic arc. At the trenches themselves, where one plate slides beneath another, sediments are scraped off the subducting plate and added to the overriding plate in structures called accretionary prisms. These prisms build upward and outward over time, adding new material to the edge of the continent or island arc, creating some of the most deformed and complex rocks found anywhere on Earth. But not all sediments are accreted. Subduction erosion is a process that removes material from the overriding plate, carrying it down into the mantle. At many trenches, subduction erosion removes up to 60% of the incoming sediment, along with fragments of the overriding plate itself, a process that can actually cause continents to shrink rather than grow. Before a tectonic plate reaches the trench and begins its descent into the mantle, it encounters the outer trench swell, a broad rise in the seafloor that forms where the plate begins to bend downward. This bending creates fractures and faults in the oceanic crust, allowing seawater to penetrate deeper than normal and beginning the process of hydration and alteration that will continue as the plate descends. The outer swell is a place of transition, where the horizontal motion of the plate begins to curve downward, where the stresses change from tension to compression, where the journey from creation at the ridge to destruction in the mantle enters its final phase. These features, these structures and processes operate on timescales that challenge human comprehension. A particle of sediment eroded from a mountain might take millions of years to reach the deep seafloor, might rest there for tens of millions of years more, might eventually be subducted and carried into the mantle where it could be melted and incorporated into new magma that rises to form new crust, completing a cycle measured not in human lifetimes but in the vast stretches of geological time. As we consider these processes, we might imagine the journey of a single grain of sand, born from the weathering of granite in a mountain range, carried by a river to the coast, swept by currents across the continental shelf, and eventually tumbling down a submarine canyon in a turbidity current to come to rest in the deep ocean basin. There it sits, accumulating a covering of other grains, of the remains of microscopic organisms that lived and died in the waters above, slowly being buried under more and more sediment. The weight of this accumulating material compresses the layers below, squeezing out water, beginning the transformation from loose sediment to solid sedimentary rock. Over time, the motion of the tectonic plates carries this sediment toward a trench, where it might be scraped off and added to an accretionary prism, or it might be subducted, carried down into the heat and pressure of the mantle where its minerals transform, where water is driven off to rise and cause melting in the wedge of mantle above the descending plate, contributing to the formation of the volcanic arc. Every rock has such a history, such a story of transformation and movement, of creation and destruction and creation again. The seafloor itself is not smooth but textured with the signatures of these processes. The abyssal plains, those flat regions of the deepest ocean basins, are smooth because they have been covered by layer upon layer of sediment, filling in the original rough topography of the volcanic oceanic crust. But where the crust is young, near the ridges, the topography is rough and volcanic, marked by fissures and pillow lavas and the fresh scars of volcanic eruptions that happened in darkness, in cold, under pressures that would crush any surface-dwelling creature. Moving away from the ridges, the crust cools and contracts and subsides, sinking deeper into the mantle, and sediments begin to accumulate, first thinly, then more thickly as the crust ages and moves into regions where more sediment rains down from above or is carried by currents from distant sources. By the time oceanic crust approaches a subduction zone, it may be covered by kilometers of sediment, a complete stratigraphic section recording millions of years of ocean history. The contrast between oceanic and continental crust is one of the fundamental observations that led to our understanding of plate tectonics. Continental crust is thick, averaging about 35 kilometers but reaching 70 kilometers beneath major mountain ranges. It is composed of lighter rocks, granites, and metamorphic rocks derived from sediments, rocks that are less dense and therefore float higher on the mantle than the oceanic crust. This difference means that continental crust is buoyant, it resists subduction, and when two continents collide, neither can sink easily into the mantle, so instead they crumple and fold and thrust over one another, building mountains that rise kilometers above sea level. Oceanic crust, being denser, readily sinks when it encounters another plate, sliding beneath continents or island arcs, descending into the mantle to depths of hundreds of kilometers before being assimilated back into the churning convection system that drives plate tectonics from below. The discovery that the seafloor was spreading was revolutionary, transforming geology from a science that viewed the Earth as essentially static, with features formed and then slowly eroding, to one that recognized the planet as dynamic, with the surface in constant motion. The evidence came from many sources. The pattern of magnetic stripes on the seafloor, symmetrical about the ridges, recording reversals of Earth's magnetic field. The age of the seafloor, youngest at the ridges and progressively older moving away. The distribution of earthquakes and volcanoes along plate boundaries. The fit of continents across ocean basins, the similarity of fossils and rock types on now separated landmasses. Together, these observations painted a picture of a planet where the rigid outer shell, the lithosphere, is broken into plates that move relative to one another, driven by the heat escaping from the Earth's interior, by the convection of the mantle, by the pull of dense slabs sinking into the depths. This motion is slow by human standards, typically a few centimeters per year, but over millions of years it adds up to thousands of kilometers, enough to close oceans and open new ones, to move continents from pole to equator, to raise mountains and create new ocean basins. The rock cycle, that great circulation of material between different states and environments, is nowhere more evident than in the ocean basins. Molten rock rises at the ridges, crystallizes to form new oceanic crust, moves away from the ridge as part of a tectonic plate, accumulates sediments, eventually reaches a subduction zone where it descends into the mantle, releases water that causes melting in the overlying mantle wedge, contributes to the formation of volcanic arcs, and is ultimately assimilated back into the mantle. Some of the material in the descending plate makes its way back to the surface relatively quickly, incorporated into the magmas that feed arc volcanoes. Some may sink deeper, perhaps all the way to the core mantle boundary, where it might reside for hundreds of millions of years before being caught up in a rising mantle plume and returned to the surface. The timescales are vast, but the process is continuous, a great engine of transformation powered by the Earth's internal heat, by the gravitational potential energy of dense slabs, by the slow but inexorable convection of the mantle. When we map the seafloor, when we measure its depth and composition, when we drill into it and extract cores of rock and sediment, we are not merely cataloging features but reading the history of our planet. Each measurement adds to our understanding, fills in details of the picture, tests hypotheses about how the system works. The fact that nearly 3/4 of the seafloor remains unmapped at high resolution means there are still discoveries to be made, still features to be found and understood, still questions to be answered about how the deep ocean basins have evolved and how they continue to change. The technology to map and study the seafloor has improved dramatically in recent decades, with multi-beam sonar systems that can map wide swaths of seafloor in detail, with autonomous vehicles that can dive to the deepest trenches, with drilling ships that can retrieve cores from beneath kilometers of water and then drill hundreds of meters into the rock beneath, with satellites that can measure tiny variations in the height of the sea surface that reveal the topography of the seafloor below, through their gravitational effects. Each new tool, each new technique, opens windows into the deep ocean that were previously closed, allowing us to see and understand more clearly the processes that shape our planet. The sediments that cover much of the seafloor are themselves archives of information. The remains of microscopic organisms that lived in the surface waters and then sank to the bottom after death accumulate steadily, forming biogenic oozes that can be hundreds of meters thick. The species composition of these remains changes with ocean temperature, with chemistry, with the circulation of currents, so a core through these sediments is a record of changing ocean conditions over time. The terrigenous sediments, those derived from land, record changes in continental climate and erosion rates, in sea level that alternately exposed and flooded continental shelves, in the configuration of ocean currents that transport fine material across vast distances. Volcanic ash layers in seafloor sediments record explosive eruptions, providing time markers that can correlate sediments across wide areas. All of this information is preserved in the layers of sediment, waiting to be decoded by scientists who know how to read the signals. The continental margins, where land meets sea, are among the most economically important regions of the seafloor. Here, beneath the sediments, we find accumulations of oil and natural gas, organic matter that was buried and transformed by heat and pressure over millions of years. Here, rivers discharge their loads of sediment and dissolved nutrients, supporting rich ecosystems in the shallow waters. Here, submarine cables carry the communications that connect continents, lying on the seafloor or buried in the sediments, vulnerable to turbidity currents and submarine landslides. The continental margins are also where most human interaction with the deep seafloor occurs, through fishing, through drilling, through the disposal of waste, through the extraction of resources. Understanding the geology of these margins, understanding the processes that shape them and the hazards they present, is not just an academic exercise but a practical necessity for managing human activities in the ocean. The forces that drive seafloor spreading and subduction arise from the interior of the planet, from the heat generated by radioactive decay and left over from the Earth's formation. This heat must escape, and it does so through the motion of the mantle, through convection cells that rise beneath ridges and sink at subduction zones, carrying plates along with them. The details of how this works, how mantle convection couples to the motion of the plates, how plates can influence the pattern of convection, these are questions that geologists and geophysicists continue to investigate using computer models, laboratory experiments, and observations from the field. What is clear is that the system is interconnected, that the creation of new seafloor at ridges is balanced by the destruction of old seafloor at trenches, that the motion of one plate affects its neighbors, that changes in one part of the system can propagate through the entire network of plates over time. The Earth's surface is not a collection of isolated features but an integrated system, where everything is connected to everything else through the motion of the plates and the processes that drive them. The abyssal plains stretch across the deep ocean floor, covering more than 50% of the entire seafloor at depths that range from 4,000 to 6,000 meters below the surface. These are the true flatlands of our planet, regions so level that they slope less than 1 part in 1,000, making them the flattest places on Earth, far flatter than any desert or prairie on land. To stand on an abyssal plain, if such a thing were possible, would be to experience a flatness almost beyond comprehension, a horizontal expanse broken only occasionally by the slight rise of a seamount or the trace of an ancient fault. This flatness is not natural to volcanic oceanic crust, which forms with considerable relief, with ridges and valleys and volcanic cones. Rather, the flatness is created by the slow, patient accumulation of sediments that rain down from above, filling in the low places, smoothing over the rough topography, creating a surface that speaks of time measured in millions of years. The process by which sediments accumulate on abyssal plains is almost unimaginably slow. We measure the rate in millimeters per 1,000 years, a pace so gradual that nothing in human experience provides a good comparison. A human lifetime might see less than 1/10 of a millimeter added to the surface, too small to measure directly, too slow to observe. Yet over the vast stretches of geological time, these infinitesimal additions build up, layer upon layer, until deep-sea sediments can reach hundreds of meters thick, creating a stratigraphic column that records the history of the ocean above and the climate of the world beyond. Each layer tells a story, captures a moment, preserves evidence of conditions that prevailed when that particular sediment was deposited. The deep ocean basins are far from the continents, far from the sources of terrigenous sediments, so what accumulates here is different from what we find on continental margins. In the most remote regions of the abyssal plains, far from any land, the sediments that dominate are pelagic clays, fine-grained particles that settle so slowly through the water column that they can take months or even years to descend from the surface to the bottom. These clays are reddened by iron oxidation, giving them a characteristic rust color that geologists recognize immediately. The reddish hue tells us about the chemistry of the deep ocean water, about the presence of oxygen that allows iron to oxidize, about the very slow rate of accumulation that gives chemical reactions time to proceed. In regions closer to continents or beneath highly productive surface waters, other sediments dominate, but here in the most remote abysses, these red clays are the characteristic deposit, the signature of distance from land and from biological productivity. The surface of these sediments, the top few centimeters, is not static despite the slow rate of accumulation. Bioturbation, the mixing of sediments by organisms living in and on the seafloor, disturbs the neat layering that would otherwise develop. Worms, crustaceans, and other creatures burrow through the sediment, seeking food, seeking shelter, and in doing so they mix the surface sediments to depths of 10 to 20 centimeters. This mixing blurs the record somewhat, smearing out events that occur close together in time, but it also oxygenates the sediments, allowing life to exist deeper within the sediment column than would otherwise be possible. The traces of this activity, the burrows and trails, can themselves be preserved if they are buried before they are destroyed, becoming trace fossils that tell us about ancient life on the seafloor. Among the various components that make up deep-sea sediments are cosmogenous sediments, particles that did not originate on Earth at all but rather fell from space. These include micrometeorites, tiny fragments of asteroids and comets that enter Earth's atmosphere, are heated by friction, and either burn up completely or, if small enough, slow down without vaporizing and drift gently down through the atmosphere and ocean to settle on the seafloor. The flux of this cosmic material is continuous, though small, adding a component to seafloor sediments that can be recognized by its chemical composition and its distinctive textures when examined under powerful microscopes. It is remarkable to think that the seafloor accumulates not just material from the land and from the ocean itself, but also material from beyond our planet, that every square meter of abyssal plain receives its share of cosmic dust year after year, century after century. The deep-sea sediments, accumulating slowly over tens and hundreds of millions of years, record approximately 200 million years of Earth history. This is not quite the full age of the oldest oceanic crust, which is somewhat older, but it represents the oldest sediments that have escaped subduction and remain available for study. These sediments preserve signals of glaciations, those episodes when ice sheets expanded across the continents and sea level fell, changing ocean circulation and chemistry, affecting the organisms living in the surface waters whose remains sink to form biogenic sediments. They preserve signals of mass extinction events, those times when large proportions of species disappeared rapidly, leaving a sudden change in the fossil record, in the types of organisms whose remains we find in the sediments. They preserve signals of changes in ocean circulation, in the chemistry of seawater, in the supply of nutrients, in the temperature of the deep ocean. The abyssal seafloor is a geological archive, a library written slowly over deep time, and learning to read it has been one of the great achievements of 20th century oceanography. Rising from the abyssal plains, cutting across ocean basins like great underwater mountain ranges, are the mid-ocean ridges, which span 60,000 to 65,000 kilometers across the globe. This makes them the longest mountain range on Earth, dwarfing the Himalayas or the Andes or any continental mountain system. The ridges are not continuous barriers but are broken into segments offset by transform faults, creating a pattern that reflects the geometry of plate motions and the behavior of the underlying mantle. The mid-ocean ridges form where tectonic plates diverge, where they move apart, and in the gap between them, new crust is created. Molten rock, magma generated by decompression melting of the mantle as it rises beneath the ridge, ascends to fill the space, crystallizing to form new basalt, new oceanic crust that is added to the trailing edges of the diverging plates. At ridges where spreading is slow, typically less than a few centimeters per year, the magma supply is limited, and rift valleys develop between the separating plates. These valleys, several kilometers wide and hundreds of meters deep, mark the actual plate boundary, the place where the plates are moving apart. The walls of the rift valley are faulted, broken by normal faults that accommodate the extension, and the floor is volcanic, dotted with recent lava flows and volcanic cones. The Mid-Atlantic Ridge, which bisects the Atlantic Ocean from the Arctic to the Southern Ocean, is a slow-spreading ridge characterized by such rift valleys. Here the plates are moving apart at a rate of about 2 to 3 centimeters per year, slow enough that the magma supply is intermittent, that volcanic eruptions are separated by long periods of inactivity, that the crust has time to cool and subside before much new magma arrives. In contrast, at fast-spreading ridges, the magma supply is more robust, and the character of the ridge is different. The East Pacific Rise, for example, spreads at rates up to 15 centimeters per year, among the fastest spreading rates known. Here there is no rift valley. Instead, the ridge crest is a broad, smooth dome, and volcanic activity is more continuous. The crust is warmer, the topography is smoother, and the seismic activity is more frequent, though generally of lower magnitude than at slow-spreading ridges. The difference in spreading rate affects every aspect of the ridge, from its morphology to its hydrothermal activity to the nature of the earthquakes that occur there. At the extreme slow end of the spectrum is the Gakkel Ridge in the Arctic Ocean, which spreads at just 1 centimeter per year, among the slowest spreading rates on the planet. Here, volcanic eruptions are rare events. Magma may ascend through the lithosphere in isolated diapirs rather than forming a continuous melt lens, and the ridge is rough and deeply faulted. The Southwest Indian Ridge, spreading at about 14 millimeters per year, falls into the category of ultra-slow spreading ridges, systems where the spreading rate is so slow that the magma supply may be insufficient to create continuous oceanic crust. In some sections of ultra-slow ridges, mantle rocks are exposed directly on the seafloor, brought up along detachment faults without a covering of basalt. These exposures provide rare opportunities to study mantle rocks in place, to understand the processes of melt extraction and crustal formation in settings where those processes are inefficient or incomplete. The ultra-slow ridges are not well understood compared to their faster-spreading cousins, partly because they are often in remote locations, like the Arctic or the far southern Indian Ocean, where access is difficult and research expeditions are rare. The forces that drive seafloor spreading at mid-ocean ridges ultimately come from deep within the Earth. Mantle convection cells, great circulation patterns in the solid but flowing mantle, drive upwelling beneath the ridges. Hot mantle material rises, partially melts as pressure decreases, and the melt ascends to form new crust while the residual mantle flows away horizontally beneath the plates. This process is continuous but not uniform. It varies in intensity along the length of a ridge, producing segments of faster and slower spreading, segments with more or less magma supply, segments with different morphologies and different levels of hydrothermal activity. Before a ridge becomes fully established, before the plates begin to separate and new crust forms, domal uplifts precede ridge magmatism. The mantle beneath begins to rise, heating and lifting the overlying lithosphere, creating broad swells that can be hundreds of kilometers across. These domes eventually rift, splitting apart to form the new ocean basin, the new mid-ocean ridge. Seismic activity at mid-ocean ridges is concentrated within a few kilometers of the ridge crest, in the zone where new crust is forming and where the crust is hottest and most actively deforming. The earthquakes at ridges are generally small, typically less than magnitude 5, because the hot crust cannot accumulate the stress necessary to generate large ruptures. It deforms too readily, through a combination of brittle fracture near the surface and ductile flow at depth. The pattern of seismicity traces out the ridge axis, marks the transform faults that offset ridge segments, and reveals the structure of the crust at depth. By studying the earthquakes, by analyzing their locations and their mechanisms, seismologists can infer properties of the crust and mantle that are not directly observable, building models of how ridges work, how magma is supplied and distributed, how the crust fractures and cools and moves away from the site of its birth. The contrast between fast and slow spreading ridges is not just a matter of rate but of process and product. At fast ridges, the magma supply is sufficient to maintain a steady-state magma chamber a few kilometers below the ridge crest. This chamber is not a liquid-filled cavern, but rather a zone where melt fraction is high enough that the rock behaves as a crystal mush with liquid percolating through it. From this chamber, magma ascends along dikes to erupt on the seafloor, building the upper volcanic section of the oceanic crust. Below the chamber, as the melt crystallizes and the rocks cool, they are split by the continuing spreading motion and carried away as part of the lower crust, creating the characteristic layered structure of oceanic crust. Pillow lavas and sheet flows at the top, a sheeted dike complex in the middle, and gabbros crystallized from the magma chamber at the bottom, all overlying the mantle rocks from which the melts were extracted. At slow ridges, this process is less regular. The magma chamber may not be permanent, may exist only during episodes of enhanced magma supply, and the crust may form in a more episodic fashion. The discovery of hydrothermal vents at mid-ocean ridges in the late 1970s revolutionized our understanding of seafloor processes and deep-sea ecosystems. Cold seawater penetrates down into the newly formed, fractured crust, is heated by contact with hot rocks and magma at depth, reacts with those rocks, dissolving some elements and precipitating others, and then rises back to the seafloor where it emerges at temperatures that can exceed 350 degrees Celsius. These hot fluids carry dissolved metals and sulfur, which precipitate when the hot water mixes with cold seawater, building chimney structures that can grow meters in height. Around these vents, entire ecosystems thrive, based not on photosynthesis, which is impossible in the darkness of the deep sea, but on chemosynthesis, on bacteria that derive energy from the chemical reactions between the vent fluids and seawater. These ecosystems include organisms found nowhere else on Earth, adapted to extreme temperatures, high concentrations of toxic metals, and the complete absence of light. The mid-ocean ridge system is not isolated from the rest of the planet's geology but is intimately connected to the global tectonic system. The new crust formed at ridges must be balanced by the destruction of crust elsewhere, at subduction zones, maintaining the Earth's surface area approximately constant over time. The rate at which crust is created at any given ridge segment can change over time in response to changes in mantle temperature, in plate motions, in the amount of volatiles like water and carbon dioxide that lower the melting point of mantle rocks. When spreading rate increases, the ridge becomes more magmatically robust, the crust thickens slightly, the ridge crest becomes smoother. When spreading rate decreases, the opposite occurs. These changes leave signatures in the structure and composition of the oceanic crust that can be read by geologists studying archaeolites, sections of oceanic crust that have been thrust onto land during collisions, or by geophysicists conducting seismic studies of the crust beneath the seafloor. The topography of the seafloor away from ridges reflects the cooling and contraction of the oceanic lithosphere as it ages. The seafloor depth increases roughly as the square root of age, a relationship that holds remarkably well for crust younger than about 70 million years. This relationship arises because the lithosphere cools conductively, like a half-space cooling problem in heat transfer, and as it cools it becomes denser and thicker, causing it to sink deeper into the underlying mantle. By measuring the depth of the seafloor and knowing the spreading rate, we can estimate the age of the crust, a technique that complements other methods like magnetic stripes and radiometric dating of dredged rocks. The depth-age relationship breaks down for very old oceanic crust, partly because the crust is buried under thick sediments, partly because other processes like mantle plumes or small-scale convection beneath the plates can perturb the simple thermal model. The global mid-ocean ridge system is a dynamic feature, responding to changes in plate motions on timescales of millions of years. Ridges can jump to new locations, segments can lengthen or shorten, transform faults can appear or disappear as the geometry of plate motions changes. The history of these changes is recorded in the seafloor itself, in the patterns of magnetic stripes, in the distribution of seamounts and fracture zones, in the ages and depths of the crust. By mapping these features and interpreting them in the context of plate tectonic theory, geologists can reconstruct the past configurations of plates, the past locations of ridges and trenches, the opening and closing of ocean basins over hundreds of millions of years. This historical perspective reveals that the pattern of plates we see today is just one frame in a long movie, that the face of the Earth has been continually rearranged throughout its history and will continue to be rearranged into the future. The sediments on the abyssal plains and the volcanic rocks of the mid-ocean ridges are both products of the same great system, the tectonic engine that drives the motion of plates and the recycling of crust. The ridges are where the system creates, where new crust emerges from the mantle, where heat and material from the Earth's interior reach the surface. The abyssal plains are where the products of this creation spread out and age, accumulate their covering of sediments, record the history of the ocean and the atmosphere in their layers, and eventually, in some cases, approach a subduction zone where the cycle of destruction will begin. Between creation and destruction lies a span of time that can exceed 200 million years, time enough for continents to drift thousands of kilometers, for species to evolve and go extinct, for ice ages to come and go, for mountains to rise and erode away. And through all of this, the abyssal plains lie in darkness and cold and quiet, accumulating their sediments millimeter by millimeter, preserving the record, waiting for the day when they will either be subducted and destroyed or, by chance, scraped off onto the edge of a continent and uplifted, preserved in the rock record on land, available for future geologists to study and interpret. The deep seafloor, both the flat abyssal plains and the elevated mid-ocean ridges, represents a realm that humans have barely begun to explore. The pressure at 4,000 to 6,000 meters depth is enormous, 400 to 600 times atmospheric pressure, enough to crush any vessel that is not specifically designed to withstand it. The temperature is cold, hovering just above freezing regardless of the season or the latitude, because the deep ocean is filled with water that formed near the poles and sank, then flowed slowly along the bottom to spread through all the ocean basins. There is no light except the bioluminescence produced by organisms themselves, no photosynthesis, no seasons in the sense we know them on land. Yet this environment is not lifeless. It supports a remarkable diversity of organisms adapted to its extreme conditions, organisms that have evolved strategies to deal with the darkness, the cold, the pressure, the scarcity of food. Some are scavengers, feeding on the remains of organisms that die in the surface waters and sink to the bottom. Some are predators, hunting other deep-sea creatures by detecting their bioluminescence or the faint disturbances they create in the water. Some are specialists, adapted to life around hydrothermal vents or cold seeps, deriving energy from chemical reactions rather than from the sun. The exploration of the deep seafloor continues, driven by scientific curiosity, by the search for resources, by the desire to understand the planet we inhabit. Every expedition brings back new data, new samples, new discoveries. The technology improves continually, allowing us to reach greater depths, to map more precisely, to observe more closely. Autonomous vehicles can now dive to the deepest trenches, withstanding pressures that exceed 1,000 atmospheres, and return with high-resolution images and samples. Tethered vehicles can stay on the bottom for hours, operated remotely by scientists on surface ships, manipulating instruments and collecting specimens with robotic arms. Seismic systems can image the structure of the crust and mantle beneath the seafloor, revealing faults and magma bodies and variations in rock properties that correlate with geological processes. All of these tools together are gradually filling in the map, answering old questions and raising new ones, revealing the complexity and beauty of the hidden world beneath the waves. Pillow basalts form the uppermost layer of the oceanic crust, created when molten lava erupts onto the seafloor and cools rapidly in contact with the cold seawater. The contrast in temperature is extreme, with the lava emerging at temperatures exceeding 1000 degrees Celsius and the water hovering just above freezing. This rapid cooling causes the lava to solidify quickly on its outer surface, forming a glassy rind, while the interior remains molten for a time, continuing to flow and sometimes breaking through the solidified crust to form new lobes. The result is a characteristic pillow shape, rounded masses that can be meters across, stacked and nested together in chaotic piles. When geologists examine pillow basalts, either dredged from the seafloor or preserved in ancient oceanic crust now exposed on land, they see these distinctive forms and recognize immediately the environment in which they formed. The pillows are not all identical. They vary in size and shape depending on the viscosity of the lava, the rate of eruption, the slope of the seafloor, and other factors that influence how the lava flows and solidifies. The glassy rinds that develop on these deep-sea basalts are more than just a curiosity of texture. They preserve information that would otherwise be lost. When lava erupts at the surface, or even in shallow water, gases dissolved in the melt can escape relatively easily, bubbling out and leaving the rock degassed. But at the depths where mid-ocean ridges lie, the pressure is so great that gases remain dissolved or form only small bubbles trapped within the rock. The rapid cooling that forms the glassy rind freezes the composition of the lava at the moment of eruption, preserving volatile gases like water vapor, carbon dioxide, and sulfur compounds. By analyzing these glasses, geochemists can measure the volatile content of the magma and infer properties of the mantle source region, track how magmas change as they ascend and crystallize, and understand the role of volatiles in melting and magma generation. The glass also preserves the isotopic signatures of the elements, providing information about the age and history of the mantle rocks from which the magma was derived. Beneath the surface, beneath the layer of pillow basalts and sheet flows, lies the plumbing system that feeds magma to the seafloor. At fast-spreading ridges, seismic studies reveal axial magma lenses lying 1 to 2 kilometers beneath the ridge crest. These lenses are not vast caverns filled with liquid magma but rather relatively thin layers, perhaps only tens of meters thick, where the proportion of melt is high enough that seismic waves reflect strongly from them. The melt fraction in these lenses may be 50% or higher, creating a crystal mush that can flow and intrude upward when the pressure conditions are right. The presence of a magma lens indicates a robust and relatively steady magma supply from the mantle below, sufficient to maintain a partially molten zone despite the cooling effects of seawater circulation through the overlying crust. At slow-spreading ridges, such lenses are absent or present only intermittently, reflecting a more sporadic magma supply. Over time, the magma within and beneath these lenses crystallizes, a process that takes roughly 100,000 years as heat is conducted away and the melt solidifies. The crystals that form are primarily plagioclase feldspar, pyroxene, and olivine, minerals that crystallize from basaltic magma as it cools. These crystals settle and accumulate, forming cumulate layers, and eventually the entire magma body solidifies into gabbro, a coarse-grained intrusive rock with the same chemical composition as basalt but a different texture because it cooled slowly enough for large crystals to grow. This gabbroic rock makes up what geologists call layer 3 of the oceanic crust, a layer several kilometers thick that lies beneath the volcanic and intrusive rocks above and above the mantle rocks below. The gabbros are not uniform. They show layering, variations in mineral composition and grain size that reflect the processes of crystal settling, magma replenishment, and fractional crystallization that occurred while the magma chamber was active. Between the pillow basalts at the top and the gabbros at depth lies a distinctive unit known as the sheeted dike complex. These are vertical or near-vertical intrusions of basalt. The oceanic crust, despite its relative simplicity compared to continental crust, is far from uniform. It varies in thickness, in composition, in structure, in age, reflecting the complex interplay of processes that create and modify it. Some sections are thick and robust, formed at ridges with vigorous magma supply. Others are thin and incomplete, formed at ultra-slow ridges where magma was scarce and tectonic extension dominant. Some sections have been intruded by off-axis volcanism, thickening the crust and altering its properties. Others have been fractured by large transform faults or bent and broken at outer trench swells. The cumulative effect of all these variations is a seafloor that, while following general patterns and obeying physical laws, is endlessly varied in detail, each square kilometer having its own unique history. Understanding the formation and structure of oceanic crust is not just an academic exercise. Beyond the active transform fault, where it no longer forms a plate boundary, the offset continues as a fracture zone that extends perpendicular to the ridge, crossing the ocean basin for thousands of kilometers. These fracture zones are not seismically active because both sides are part of the same plate, moving in the same direction, but they remain as topographic features, as scars in the seafloor that record the ancient plate boundary. The fracture zones often appear as linear valleys or ridges, the result of vertical motion that occurs because the crust on the two sides has different ages and therefore different depths, having subsided by different amounts as it cooled. The younger side of the fracture zone is shallower, and the older side is deeper, creating a topographic step that can be hundreds of meters high and persists across entire ocean basins. Some fracture zones are enormous in scale. The Romanche fracture zone, for example, offsets the mid-Atlantic ridge by 900 kilometers, making it a prominent feature. Marine magnetic mapping, conducted systematically across the ocean basin starting in the 1950s and continuing to the present, confirmed plate tectonics by showing that the pattern of magnetic anomalies matched the predictions of the seafloor spreading hypothesis. The maps revealed symmetric stripes, offset by fracture zones in ways that made sense given the geometry of plate motions, and the ages derived from the magnetic anomalies matched other independent estimates from fossils in sediments and from the depth-age relationship of the seafloor. This convergence of evidence from multiple sources, all pointing to the same conclusion, made the case for plate tectonics overwhelming and led to its acceptance as the unifying theory of geology. At the mid-ocean ridges, where new crust is forming and where the crust is hottest, another remarkable phenomenon occurs. Hydrothermal vents form where seawater circulates through the hot crust, driven by the heat of recent magmatism. The process begins when cold seawater percolates down through fissures and fractures in the volcanic rocks, penetrating perhaps 1 to 2 kilometers into the crust. As it descends, it encounters hotter rock, and its temperature rises. The water can reach temperatures exceeding 400 degrees Celsius, far above the boiling point at surface pressure, but it remains liquid because of the immense pressure at depth. At these high temperatures, the water becomes a powerful solvent, reacting with the rocks it contacts, dissolving some minerals and precipitating others. During this heating and reaction, magnesium and sulfate are stripped from the seawater, removed by reactions with the rocks. At the same time, other elements are leached into the fluids. Sulfur from the mantle and crust dissolves, as do iron, manganese, copper, and zinc. When this superheated, mineral-rich fluid rises back to the seafloor and mixes with the cold, oxygenated seawater of the deep ocean, the minerals precipitate, forming the dramatic chimneys and plumes known as black smokers. Far from the mid-ocean ridges, on the flat abyssal plains where sediments accumulate slowly and life is sparse, another type of mineral deposit forms. Manganese nodules grow on the seafloor, strange potato-shaped concretions that can range from a few centimeters to tens of centimeters in diameter. These nodules form extremely slowly, accreting layer by layer at rates measured in millimeters per million years, among the slowest geological processes known. Despite this slow growth, the nodules can become quite large given enough time, and they cover vast areas of certain abyssal plains in densities that can reach tens of kilograms per square meter. The nodules accumulate metals from seawater, concentrating elements like cobalt, nickel, and manganese that are present in seawater at very low concentrations but that, over millions of years, can be extracted and incorporated into the growing nodules. The mechanism by which nodules grow is not entirely understood, but it involves a combination of chemical precipitation and biological mediation. Microorganisms living on and within the nodules may play a role. Many seamounts remain unexplored. The deep ocean is vast, and the resources to map and study it in detail are limited. Most of what we know about seamounts comes from a small number that have been studied intensively, and there is no reason to think that these are representative of the tens of thousands that exist. Each new seamount explored has the potential to reveal new species, new geological features, new processes. The exploration of seamounts is an ongoing endeavor, driven by advances in technology that allow us to map the seafloor at higher resolution, to dive deeper and stay longer with submersibles and robots, to sample and analyze rocks and organisms more effectively. As this exploration continues, our understanding of seamounts and their role in the ocean system will continue to grow. The mineral deposits, the seamounts, the volcanic islands, all are products of the dynamic processes that shape the ocean floor. The mantle provides the heat and the material, plate tectonics provides the framework and the motion, and the interaction of molten rock with seawater and sediments and biological systems creates the rich variety of features we observe. Each feature tells a story, records an event, preserves evidence of the conditions under which it formed. Reading these stories, interpreting this evidence, is the work of marine geology, a field that combines direct observation with remote sensing, sampling with modeling, geology with geophysics and geochemistry and biology. The ocean floor is not a simple or uniform place but a complex landscape shaped by forces operating on timescales from seconds to hundreds of millions of years, a landscape that continues to evolve, continues to surprise, continues to challenge our understanding. Oceanic trenches form exclusively at subduction zones, those places where one tectonic plate descends beneath another, bending downward and sinking into the mantle. The trenches mark the surface expression of this descent, forming elongated depressions in the seafloor that run parallel to the volcanic arcs or continental margins where subduction occurs. These are not subtle features but dramatic ones, the deepest places on Earth, where the seafloor plunges to depths that exceed anything found on the continents or in the rest of the ocean basins. The formation of a trench begins when two plates converge and one, typically the denser oceanic plate, begins to sink beneath the other. As it bends downward, it creates a depression, and this depression becomes the trench. The depth of the trench depends on many factors: the age and density of the subducting plate, the rate of convergence, the amount of sediment filling the trench, and the angle at which the plate descends. The deepest parts of the trenches, those regions exceeding 6,000 meters depth, are called hadal zones. Near the surface, the outer walls of trenches are shaped by bending faults, normal faults that form as the plate bends downward before subduction. These faults break the seafloor into a series of horsts and grabens, creating a rough topography on the outer trench wall. The faulting allows seawater to penetrate deeper into the plate than it otherwise could, hydrating the oceanic crust and even the uppermost mantle, changing their mineralogy and properties in ways that are important for what happens later when the plate descends. The inner wall of the trench, the side toward the overriding plate, often shows a different character, sometimes with sediments accreted from the subducting plate, sometimes with steep slopes mantled by debris from landslides and turbidity currents originating higher on the slope. Trench environments are among Earth's most extreme, combining great depth, high pressure, low temperature, and isolation from the surface. Yet even here, life persists. The organisms in trenches include amphipods, snailfish, and various microbes, all adapted to conditions that would be lethal to surface-dwelling organisms. These hadal organisms have evolved special adaptations: proteins and cell membranes that function under high pressure, enzymes that work efficiently at low temperatures, mechanisms to deal with the scarcity of food that characterizes the deep sea. Studying these organisms provides insights. The types of sediments that accumulate on the seafloor vary with depth, with distance from land, with the productivity of the overlying waters, and with the chemistry of seawater. Pelagic carbonate sediments, composed of the calcium carbonate shells of planktonic organisms like foraminifera and caccolithophores, accumulate in the open ocean where the organisms live in the surface waters and their shells sink after death. However, these carbonate sediments dissolve if they sink below a certain depth known as the carbonate compensation depth, or CCD. Below the CCD, the seawater is undersaturated with respect to calcium carbonate, meaning that the carbonate minerals dissolve rather than accumulating. The CCD varies with location, typically lying at depths of 4 to 5 kilometers in the modern ocean, deeper in the Atlantic than in the Pacific, shallower at high latitudes than in the tropics. Above the CCD, carbonate sediments can accumulate, forming foraminiferal oozes, soft sediments composed mostly of foram shells, recording the history of surface ocean conditions through changes in the species present and in the isotopic composition of their shells. In regions where the seafloor lies below the CCD, carbonate sediments do not accumulate, and instead, siliceous sediments may dominate if the surface waters are productive. Radiolarian and diatom oozes form where these organisms are abundant, the radiolaria in equatorial and subpolar regions, the diatoms particularly in the high latitudes where nutrients are plentiful and diatoms thrive. Siliceous sediments, however, also dissolve, though the process is different from carbonate dissolution. Silica is undersaturated throughout most of the ocean, so siliceous shells begin dissolving as soon as they leave the surface waters. Most of the silica produced by organisms is dissolved before it reaches the seafloor, and only in regions of very high productivity does enough silica reach the bottom to accumulate as sediment. Even after deposition, siliceous sediments continue to dissolve, the silica reprecipitating in more stable forms over time, turning the soft ooze into chert through diagenetic processes that take millions of years. The chemistry of deep-sea sediments reflects ocean circulation, the movement of water masses that carry dissolved nutrients, carbon, oxygen, and other properties from one part of the ocean to another. Changes in circulation, driven by climate or tectonic changes, alter the distribution of nutrients, affecting where organisms can thrive, and alter the chemistry of deep water, affecting where carbonates and silicates can accumulate. By studying sediment cores, geologists can reconstruct past ocean circulation, identify times when deep water formation shifted from one region to another, trace the effects of ice ages on ocean chemistry, and link oceanic changes to changes on land and in the atmosphere. The sediments are archives, recording information about the past in their layers, in their compositions, in the fossils they contain, and in the isotopic signatures of their minerals. The deep ocean, with its trenches and seeps and varied sediments, is a world that remains largely unknown despite decades of exploration. Each expedition brings back new data, answers some questions, raises new ones. The technologies improve, allowing us to go deeper, stay longer, sample more precisely, measure more accurately. Yet the ocean is vast, and the resources for exploration are limited, so progress is incremental, each discovery adding a small piece to the larger picture. The trenches, the deepest parts of this deep realm, are particularly challenging, accessible only to specialized equipment, visited only occasionally. What we know about them comes from a handful of dives, a scattering of samples, remote observations from surface ships. There is much more to learn, many more discoveries waiting in the darkness, many more questions to answer about how these extreme environments function, how they fit into the global system, how they have changed over time, and how they will respond to changes occurring now as human activities alter the chemistry and temperature of the ocean. The trenches, ridges, and plains of the deep ocean are not isolated features but form a connected system, parts of a global network driven by the movement of tectonic plates. What is created at the ridges must eventually be balanced. The seafloor shapes earthquakes and volcanoes worldwide. The geometry of subduction zones, the nature of the seafloor being subducted, the sediments filling the trenches, all affect where and how earthquakes occur, how large they can be, whether they generate tsunamis. The great earthquakes that threaten coastal populations occur mostly at subduction zones, where oceanic crust descends beneath continents or island arcs. The volcanoes of the Ring of Fire, the arcs that surround the Pacific Ocean, are fed by magmas generated when water released from subducting oceanic crust causes melting in the overlying mantle. Understanding the deep sea processes, the formation of oceanic crust, its alteration by hydrothermal circulation, its structure and composition, is essential for understanding and predicting these hazards that affect millions of people. Each feature of the deep seafloor, from the smallest abyssal hill to the largest oceanic plateau, from the pillow basalts at ridge crests to the sediment cores from the deepest trenches, reveals something about Earth's internal dynamics. The patterns of magnetic stripes tell us about the history of the magnetic field and the motion of plates. The composition of basalts tells us about the temperature and composition of the mantle. The distribution of earthquakes reveals the geometry of descending slabs. The chemistry of hydrothermal fluids informs models of water-rock interaction at high temperature. The fossils in sediments record past climates and extinctions. Every measurement, every sample, every observation adds to our understanding, constraining theories, testing models, sometimes confirming expectations and sometimes surprising us with the unexpected. Despite all that has been learned, much of the deep ocean remains unseen. The maps we have are improving, with satellite altimetry providing global coverage at moderate resolution and ship-based multi-beam sonar providing detailed maps of limited areas, but vast regions have never been mapped at high resolution. The rocks of most of the seafloor have never been sampled. The biological communities over most of the deep ocean have never been surveyed. The number of dives to the hadal zones can be counted on two hands. The deep ocean is not just deep in the vertical sense but vast in the horizontal, covering more than 60% of Earth's surface, most of it far from any coast, accessible only by ships that are expensive to operate and limited in number. The challenges of exploring the deep sea are not just technical but logistical and financial, requiring sustained commitments of resources and personnel over years and decades. Future exploration will reshape geological understanding in ways we cannot fully predict. Every major advance in technology has led to new discoveries that changed how we think about the deep sea. Echo sounders revealed the mid-ocean ridges. Magnetometers revealed the magnetic stripes that led to plate tectonics. Submersibles revealed hydrothermal vents and their ecosystems. Drilling revealed the structure of oceanic crust and the sedimentary record of climate. Each new tool, each new approach, opens windows that were previously closed, allows us to see what was hidden, to measure what was unmeasurable. The technologies under development now, the autonomous vehicles that can map and sample without human presence, the sensors that can be deployed for years to monitor seafloor processes continuously, the genetic techniques that can identify organisms from traces of DNA in seawater, all promise new insights, new discoveries, new understanding. The deep sea is Earth's largest geological frontier, the last great unexplored realm on our planet. While we have sent probes to Mars and beyond, while we have mapped the surfaces of distant moons, we know less about our own seafloor than we know about some planetary surfaces. This is not because the deep sea is unimportant or uninteresting, but because it is difficult to access, because water absorbs light and radio waves, because pressure increases with depth in ways that challenge engineering, because the ocean is vast and the resources for exploration are limited. Yet the deep sea is worth exploring, not just for the resources it may contain or the hazards it may help us understand, but for its own sake, for what it can teach us about our planet, about how the Earth works, about the history written in stone and sediment beneath the waves. As we close this geological tour of the deep sea, we might reflect on what these places mean. They are far from human experience, beyond the reach of sunlight, yet they are intimately connected to the life we know. The seafloor regulates the chemistry of the ocean, stores carbon that affects the climate, and records the long-term history of the Earth's evolution and structure. Geology isn't just about mountains and earthquakes and the formation of continents. It's also about the coffee cup you're holding, the chair you're sitting on, the building around you, and the countless mineral-derived materials that make modern life possible. Every object is a geological specimen. Every day is a lesson in earth science, if you know how to look, if you remember to pay attention. The Earth provides everything we use, everything we touch, everything we build. We are not separate from the planet but deeply embedded in its systems, dependent on its resources, shaped by its constraints. The minerals we extract and use will eventually return to geological cycles, perhaps to be concentrated again in some future or deposit, perhaps to become part of some future civilization's technology. The atoms are conserved even as their arrangement changes. The elements persist even as they move through different forms. And in this great cycling of materials, this endless transformation and reorganization, we find both our place in nature and our connection to deep time, to the long history of the Earth and the even longer history of the cosmos. When you go about your day tomorrow, perhaps you'll see the objects around you a little differently. Perhaps you'll recognize the geological heritage in everything you touch, and perhaps that recognition will bring a quiet sense of wonder at how intimately we're woven into the fabric of the planet. In the quiet of the abyss, in the cold and pressure and darkness, the Earth's processes continue as they have for hundreds of millions of years, indifferent to whether we observe them or not, operating according to physical and chemical laws that we are still working to fully understand. The seafloor spreads, subducts, accumulates sediments, hosts life, cycles elements, stores carbon, preserves history. It is ancient and yet constantly renewing, familiar in its adherence to natural law and yet full of surprises when we look closely. It is worthy of our attention, our respect, our curiosity, and our care as we learn to explore it, to understand it, and to live in harmony with the ocean that covers most of our blue planet. The deep sea waits, patient and enduring, ready to reveal its secrets to those willing to venture into its depths, to ask questions of its rocks and sediments, to listen to the stories it has been telling for longer than humans have existed, stories of a planet alive with change, a planet where creation and destruction are two sides of the same process, a planet where everything is connected through the grand cycles of geology, chemistry, and life.